Yes, it can hear me. All right, how is everyone doing today? All right, okay, good. Okay. So for the extra credit activities, there are going to be two. So one is going to be completion-based, and one will be credit-based. So the one that is going to be completion-based will be a metacognitive activity, which is basically, I want you to reflect on every single question on the exam, and I want you to go through and identify why you made that error. So whether it was I just forgot this, I don't remember us ever learning that, I just wrote the wrong thing, whatever it is, I want you to go through and actually assess every single question. So then you will just go through, complete the activity, and then you will upload it, and it'll just be, did you do it? Cool, you get free points. So that'll be the one activity. The other one is going to be in Achieve. So it'll be essentially another homework assignment, but it'll be based on the same chapters that Exam 2 is based on. So it'll be chapters 6, 7, 8, 9, and 11. And it'll be a homework assignment based on those. And the idea is that there will be you'll be able to reattempt questions like you can on the homework, but there'll be a greater penalty for guessing. So it'll be a 25% per wrong answer on each question. So that way I don't want you to spend, you have enough other assignments. I don't want you to spend forever on this, but it is worth points. So I do want you to ultimately learn everything. So that'll be that. I had it created, and then I refreshed my computer right before lecture, which is actually why we're starting a little late, and I can't find the assignment in Achieve anymore. So I will have to recreate it. Because I was hoping to show it to you, but I don't know what happened to Achieve. So that'll be in Achieve. Both of the assignments will be due on reading day. So you'll have 2.5 weeks to do them. That'll be that. So they will be posted by Monday, and then you'll have until the end of day on reading day to upload them. Because it'll be due on reading day, and we're so close to the final exam and trying to get grades in, they will not be accepted late. So you want to make sure that you do them either early or as best as you can. So the one in Achieve will be able to be eligible for partial extra credit. So it'll just be however many points you earn is how many points you get. So if you only get half of it done by reading day, then cool, you get half of the extra credit points. Yeah, so that will be the plan. Are there any questions? Yes. That is a great question. That I hadn't actually done the math on yet. So for the question of how many points will you actually be getting back, my initial thoughts, although I might change this once I reassess, doing the math of trying to fix the average, but what I was currently thinking was it would be 10 points for the metacognitive activity, 20 points for Achieve. So that you could get 30 points back on the exam, which could boost your grade by 15%. Cool. All right. Any other questions? Yeah. Yeah, so the recording for tonight's review session will be posted. So it's recorded within our Canvas page. So the recording will be automatically uploaded. It'll take a while for it to process. With a 3-hour, I'm anticipating about 3-hour long video, it'll probably take about 1.5 hours to 2 hours for it to actually get up there. But it'll automatically upload to the Canvas Carmen Zoom tab. And so if you go Carmen Zoom and then Cloud Recordings, it'll be in there automatically. And then I will also, once the link is created, I will then create a link to put it into the module with the exam, where the study guide and answer key and all of that is. I'll put a link to the recording in there as well. So it'll be both automatically put into the Carmen Zoom tab or the Canvas Zoom tab or whatever it's called. And then I will create another link in the modules. Any other questions? So yes, that review of the exam will be at 4 o'clock tonight. It is just via Zoom, so it is totally on Zoom. I don't know what, remote, there we go. And yes, it'll just be online. There's no like physical place to meet, but it will be entirely recorded. So you can also like come and go if you want, like if you can only be there for 30 minutes, cool. You can hang out for 30 minutes if that's, so you can catch part of it. That's totally cool. You don't have to be there the full time, but the recording will be made available for the full time. Do we have any other questions? Right. Since we actually are talking about due dates, I do just want to, one, point out that our final exam is on Monday, December 9th. So it's the second day of finals. So that's this day. So we are right here. So we're not in chapter 13, but that's fine. It doesn't matter. So our chapter 12, which we're going to finish today, that homework is due this Sunday. And you also have quiz 7 due this Sunday. So quiz 7 is based on all material since the last quiz, but I'm going to emphasize that since I'm giving you another, whatever, I'm just going to tell you, it's only based on chapter 12. So there you go. I mean, you still have to, be aware of everything else, but really I'm focusing on the Alkene editions. That's the point of that quiz, is to make sure you have your Alkene editions organized. So that's going to be the quiz that is due this weekend. I did update all of the SLDS time accommodations, so if you don't see that time, let me know. And I did actually for both future quizzes, but so that's where we're looking for right now. That's going to be due this weekend, so you do have assignments due this weekend. And then I had updated, I think I did. I've been trying to update Canvas with the survey completions because I was able to modify Canvas to allow me to show complete or incomplete. So if you see on the surveys that yours was marked incomplete and you're like, but I did it, contact me and then we'll update it. And then, yes, and then this will be where your extra credit is due. It'll be due at 11:59 p.m. on reading day. Cool. All right. Any questions now that we kind of see our schedule? All right, sweet. Oh, another thing about the extra credit, and I will write up a list of like rules and expectations, but basically, the most important thing to me is that you understand the material. So I'm gonna let you like talk to each other. You can work on it together. You can work on it with TAs. You can work on it with me. We can do it in office hours. Like I want you to get the right answers. So the idea is I want you to get the points. So yes, so that'll be basically you can use any tool accessible to you, people, online, everything, when working on the extra credit. But I'll write all that up for you for Monday. Great. Okay, let's finish chapter 12 then. Okay. So we had left off looking at our syn addition mechanisms. So we had talked about our 5 different types of syn additions. And actually, remind me, what are the 4 mechanistic classes of our alkene additions? Syn, yeah, one of them syn, so that's one of them, the one that we're talking about right now. Anti, carbocation, and then the one we haven't gotten to yet, oxidative cleavage. So you want to make sure that you know that these are the classes that we're falling into. So right now we're talking about those syn additions. Syn is describing the product, right? It's saying that you end up with the elements, the new groups are on the same side in the end of that step. So for the mechanism, that mechanism, when we're looking at it, it was that our alkene is attacking the electrophilic atom, and then the bond of our electrophile is actually going to come back and attack that carbon, the more substituted side. So for the hydrogenation, we're just hydrogen and hydrogen, right? And then it's just, that is your entire mechanism for the hydrogenation. Like it's just, that's it. Remember, for hydrogenation, you must have palladium. The metal catalyst is necessary. So if you look on certain websites and books and, I don't know, talk to certain people, they like to illustrate it where you have, like, this is your palladium surface, and then they show that palladium is the one that's actually splitting the hydrogen-hydrogen bond, and then that is what is actually reacting with your alkene. So that it's actually, you're attacking the hydrogen, the electrons go onto the palladium, and then that's the bond coming back. If you want to show it that way, cool. I'm all right with you just knowing the role of the palladium, that it's lowering the energy of activation barrier, and this being your mechanism that you show. Like, I'm okay with you keeping the same arrows for all of our syn addition mechanisms, right? So some books, but I'm okay with just that, right? I'm okay if you don't actually try to show palladium as a surface that's actually like facilitating this. As long as you know that you must have palladium and that its role is lowering the energy of activation barrier, and so it's making the reaction possible. Without palladium or platinum or whatever your metal catalyst is, without a metal catalyst, it doesn't happen. You don't add hydrogen across the double bond. Okay, so that was where we left off with our hydrogenation. So let's look at our specific steps for our hydroboration. I told you that hydroboration was a two-step reaction. So it's the hydroboration oxidation. The first step is hydroboration. We're adding hydrogen and boron across our double bond. So that is the syn addition. So it's going to be those same arrows. Which is my electrophilic atom in BH3? What's going to be the Lewis acid? The boron. Remember, boron, when it's neutral, boron is sp2 hybridized. Boron has an empty p orbital. Boron and aluminum, they're hypovalent, meaning that they're really good Lewis acids. They have an empty p orbital, they only have 6 valence electrons, so they're okay just taking electron density. So that boron is going to be our electrophilic atom. So we're going to be attacking that boron because it has an empty p orbital. So then my nucleophilic site is that bond, and that's what's attacking back down. So electronics are helping to control this. A major reason why we're getting, and actually more important than electronics, is actually sterics. So sterics is the major factor of our regioselectivity here. So because of the fact that boron is larger than hydrogen, literally everything is larger than hydrogen, except for subatomic particles, but like all of our elements are bigger than hydrogen. Hydrogen is the smallest. So it's because this has to happen all in one step, just like how SN2 was all one step, sterics matters. When it's concerted, sterics matter. So that boron, the BH2, the bigger thing, has to go where it fits. It's going to go on the side where there's more space. So that's the biggest reason that we're actually observing this regioselectivity here, is boron's bigger, so it has to go on the side where it fits better, on the side with less substituents, or fewer substituents. So then the hydrogen goes on the more substituted side. Cool. That's the syn addition. So the syn addition, pretty straightforward. That's it. It's just, those are the two arrows, and it just sits down on top of, it's weird, sits down on top of our alkene and on the bottom. So remember, plus our enantiomer. Right, so we would get plus that structure, plus where the boron's on the bottom as well. Step 2, so this is the product of step 1. Step 2 is the oxidation. So step 2 is going to be where we're going to turn that boron, the BH2, into an OH. The mechanism of this is you don't need sodium hydroxide, but sodium hydroxide is going to make this faster. So the reason sodium hydroxide is going to make it faster is because that peroxide, I need it to be a nucleophile. Remember, boron is still going to be an electrophile. Boron right now is neutral. Boron still has an empty p orbital. This boron is electrophilic. So I need this oxygen to be a nucleophile. That peroxide has to be a nucleophile. So to make it a better nucleophile, let's make it anionic. Let's give it a negative charge. So if I have it do the deprotonation, I get this acid-base chemistry. Where I make that hydroxide, or the peroxide anion, and water. Which side of the equilibrium is favored? Let me ask this another way. Is hydrogen peroxide or water going to be the stronger acid? The hydrogen peroxide is going to be the stronger acid. Yes, why? We have 5 factors. So what's the first factor? Charge. Is there a difference between charges? No. So then we go to atom. What atom is the hydrogen directly connected to? Oxygen. Is there a difference? No, so it's not atom. Then we go to resonance. Do I have any resonance structures? No, there are no double bonds, right? So if there are no double bonds, it's not going to be resonance. What's next? Induction. Is there a difference in the elements that are attached? Yes. So what is the difference? I have this extra oxygen, right? So this oxygen is going to help pull electron density away, which is going to make this hydrogen even more acidic. So here I have inductively withdrawing forces, making that hydrogen more acidic, or you could think of it as it is helping to stabilize that conjugate base. So this is my weaker base, but it's going to be still a good nucleophile because it's negatively charged. So this is the better nucleophile than H2O2. And my equilibrium lies in favor of these products because this is going to be, this is a weaker base than hydroxide because of inductive forces. Okay. So all we did was made a better nucleophile. We didn't do anything special yet. So the next thing that we need to actually do is have nucleophile attack the electrophile. So the O-, the nucleophilic atom, is going to, I'm going to have a kind of a long arrow, I'm sorry. It's got to come around and attack that boron, right? So I made a nucleophile, I made my electrophile, now I gotta make them meet. And so then that's what we're seeing here, is just, I made a bond between the oxygen and the boron. Boron now has a negative charge. I didn't need another arrow because boron is hypovalent. I don't exceed its octet, so I can just draw an arrow directly from oxygen to boron, and that's it. Now, when I look at this, my oxygen here, that oxygen is going to be electrophilic, because especially if I'm in hydroxide right now, if I'm in a basic condition, then OH can be a leaving group. My nucleophile is going to be this carbon-boron bond. I have to do a rearrangement in order to make this new carbon-oxygen bond. This is the step that most students forget in the mechanism, but it is the important step because this rearrangement is what is ensuring our stereo retention. Meaning, the oxygen is directly replacing that boron. It's making sure the stereochemistry stays exactly the same. Where I had that boron, we are directly wiping it out and putting an OH on the same side, right? So my nucleophilic bond is going to be attacking that oxygen, and then I'm going to push the electrons onto the OH. So what these arrows are saying are that I am making that carbon bolded oxygen bond. I am breaking my carbon boron bond and the bolded oxygen normal oxygen bond. That's what those arrows are telling me. So when I do this, essentially what I'm doing is I'm erasing this bond, drawing a connection to this oxygen, and then erasing that leaving group. So when I do that, I'm now putting that boron on the outside so that I'm now getting that rearrangement. So I have carbon oxygen boron instead of carbon boron oxygen. Right? Do we see how it's shifting like that? Okay. So at this point, so that's kind of the weird step. This is usually the step most students forget and throws off their entire mechanism. So then the next step is going to just be, we got to get rid of this boron. Well, that boron is electrophilic again. It's now neutral again. Then my hydroxide is going to be a potential nucleophile. So I'm going to have my hydroxide that I just generated now attack that boron and kick out that oxygen that was that original peroxide oxygen. That was this oxygen. That's the one that ends up in the ring, and then you just do proton transfer, just acid base, get it neutral. So the first step of our hydroboration oxidation is just a normal syn addition. Step 2 is this, a lot of like Lewis acid base reactions, and then like just normal nucleophile electrophile with that weird rearrangement in the middle, where you have to end up with that carbon directly attached to the oxygen and kicking out the boron and like disconnecting the boron. Are there any questions about hydroboration oxidation? So it'd be that plus the enantiomer. You'd have it for both molecules. And on a mechanism question on the final, I wouldn't ask you to draw the mechanism twice. So I would give you a specific enantiomer and say, show the arrows to make that one, right? So then you just make one of them, you wouldn't do it twice. On a predict the product, I would want you to draw both products. All right. For our osmium tetroxide, this one is going to be a little bit strange, and it'll be the same sort of thing for our cold potassium permanganate. Remember, potassium permanganate is really reactive, so you got to have something to slow it down if you want to stop at the dial and not make a carboxylic acid. Potassium permanganate wants to make carboxylic acids out of everything. So in order to get it to stop, we had to make it cold or dilute. So the arrows are going to be the same, it's just that you would have manganese in the middle instead of osmium. So it's going to be our alkene is going to attack one of the oxygens. That's going to push the electrons onto the osmium. And then our other pi bond is going to come down and attack it. This is what's known as a 4+2 cyclization. The reason it's called that is because it's an addition that involves 4 pi electrons adding to 2 pi electrons. So my 4 pi electrons are here. Well, I guess we'll use the bonds we draw arrows from. So those are 4 pi electrons that are involved. And then here we have our 2 pi electrons. So we just have this extra arrow where we're actually putting electrons onto the osmium. We're putting it onto the transition metal. So we still have in general that our double bond is attacking the one element, the other bond comes back down. We just have this new arrow in the middle that's different for osmium tetroxide. But it's still a syn addition. It's still adding to the same face. So we get to this cyclic intermediate, which then you don't need to know the mechanism of, just know that it adds water and it goes to the end. And it's going to, water is going to release it. But you end up with that dial plus your enantiomer, because it would add to both the top and the bottom, or both the front and the back. Any questions about osmium tetroxide? So. Don't need to know that mechanism to actually release the osmium. Next up, we have our MCPBA. So this is MCPBA. This is metachloro peroxy benzoic, bless you, acid. So what this is telling us, meta, is going to indicate that we are 1,3 di substituted. So it's telling us that I have that relationship where the chlorine and the other substituent on benzene are 1,3 away. So they're not right next to each other, they're 1 away from each other. That's meta. Chloro is telling me one of my substituents is chlorine. Peroxy is telling me that I have that oxygen-oxygen bond. Benzoic, well, I guess benzene, the benz, is telling me that I have benzene. The oic acid is telling me I have that carboxylic acid. So that's what I'm seeing, is I have benzene that is 1,3 di substituted. One of the substituents is a chlorine. The other would be a carboxylic acid, but it gets an extra oxygen. That's MCPBA. This is what's known as a per acid. So a per acid, that should be benzoic acid. So a per acid is just a peroxy acid. meaning it is a carboxylic acid that has an extra oxygen. That's all that's saying. So anything that is a peracid will be able to do this reaction. MCPBA is just like commercially available. It's easy to buy. It's pretty cheap. It's pretty stable. So it's a nice reagent you can just pull off a shelf. Actually, it's usually kept in a freezer, but you can work with it. So it is just going to be like any of them will work. So even if you have like literally anything, this is the important part. That carboxylic acid with an extra oxygen, that's the reactive, that's the business end. That's the side that's actually doing it, doing the reaction. This reaction is exceptionally well studied. So this is one of the few mechanisms that actually they have really looked at every single step. They looked at every single aspect of this mechanism, and they know exactly what's going on. This mechanism has 4 arrows, which is going to be weird because normally, whenever you're doing a mechanism, you normally don't want more than 3 curved arrows in a step. Normally, if you draw more than 3 curved arrows in a step, you're probably doing too much in a step. So in most of your mechanisms, if you look on an exam, I normally, if I grade your mechanism question, I didn't this last exam, but normally when I grade the mechanism questions, if you have a lot of arrows, I'll usually circle it and be like, no, too many. That's too many arrows. This is the difference. So here, I'm now gonna have 4 curved arrows, and it's really well studied to know I have all 4. It is still going to be that my alkene is where I start. You start from the alkene, you attack out. The electrophilic site is that oxygen. That is going to be my electrophilic atom. So my alkene is going to attack that oxygen. The reason why is because this whole thing is going to be my leaving group. Because it's going to be resonance stabilized, so it's going to be a weak conjugate base. It's a good leaving group. So this is just your leaving group, which is a really massive leaving group, but whatever, it's still just a leaving group. So we're going to be breaking that bond so that we are taking the electrons from the oxygen-oxygen bond, and we're going to push it over and make a new oxygen-carbon double bond. So the electrons are going to go from that bond, hop over. Because carbon can't make more than 4 bonds, this pi bond is reaching over to take that hydrogen. So then as it is taking this hydrogen, it is making this bond more nucleophilic. Basically, these electrons are where the heck do I go? Because right now, we're accounting for everything except for these electrons. These electrons are what come back down. So this is the syn addition being facilitated by that leaving group. So you actually have all 4 arrows. Yes? So the hydrogen is, the hydrogen actually isn't. So it's going to the more substituted side because this is the nucleophilic side. This is nucleophilic, this is more electrophilic side. Thinking of if we were to form a carbocation, it would be more stable on the more substituted side. So that's why when we're attacking down, we always attack the more substituted side. So the bonds that we're making, though, are that we are making, do I have it on the next? No. We are making a 3-membered ring to this oxygen. That oxygen is that end oxygen of your peracid. So when we take, because this pi bond is what's taking that hydrogen, it's taking it away, oops, is taking this away so that this is, like that whole thing is breaking off. And so that one oxygen is what's sitting back down. That's what's sitting on top of it. So they've studied it to see that it's like really organized. It actually is like it closes itself up, sits that oxygen right on top, and then you get your leaving group. I don't know why my carboxylic, my benzene looks so bizarre, but whatever. That's the byproduct. And it'd be this plus your enantiomer. Oops. Because remember, it can happen on the top and the bottom. So it's still a syn addition, it just has a couple extra steps. Any questions about the MCPBA? Okay. So to summarize our syn additions, they are adding to the same face of the alkene, meaning stereospecific. So you're getting the elements adding to either the top or the bottom, and you get both happening. It is concerted. This BH3, this hydroboration oxidation, this is our first anti-Markovnikov addition that we've seen. This is the first time where the oxygen ends up on the less substituted side. And it happened because of the syn addition where boron needed to go on the side where it had more space. So this led to our anti-Markovnikov alcohol product. When we talk about radicals, we will get one more anti-Markovnikov addition, but at the moment, this is the only one we know. That hydrogenation required a metal catalyst, and the more electron-rich alkenes are going to be what react with MCPBA first. This is actually true for all of our reactions because we're adding electrophiles to all of them. But the thing to note is that MCPBA, this is an electrophilic source of oxygen. So if you have multiple alkenes, whichever one is more substituted, meaning it has more electron donating groups coming in, that means it's more electron rich. That's what reacts first. So if you only have one equivalent of MCPBA, you react with the more substituted alkene first. If you have excess, you react with everything. Now on to our last category, our oxidative cleavage. So the oxidative cleavages are going to look kind of weird. Their mechanisms are they're not really as similar to the other ones. I mean, I guess the potassium permanganate one is kind of similar, but the ozonolysis is going to look very different. So ozonolysis is where we are going to be adding ozone, O3, across our ring. Oxidative cleavage is where we are literally cutting this double bond in half. We are going to take this double bond. We cut it in half. We are going to pull these pieces apart so that I am just pulling the carbons apart. And then I'm going to insert double bonds to oxygen where I had that original pi bond, right? I am just cleaving it. I am cutting it in half and putting carbonyls where I had the alkene. And that's what I'm seeing right here, is that I'm getting these carbonyl products. DMS is dimethyl sulfide. So it is SCH32, or it is that Me2S, however you want to write it. It is a reductant. If you have a reductive second step, this is what's going to give you ketones and aldehydes. If you have an oxidative second step, so if you do ozone and then you do hydrogen peroxide, That's going to make ketones and carboxylic acids. So the key difference is if it's reductive, then you're adding in hydrogen. You're ending with that hydrogen there. If it's oxidative, you get no H. So that second step is controlling it on your side where you had a hydrogen. So if it's already like di-substituted, if you already have 2 carbons, you keep 2 carbons, right? So it's only if you're starting with a hydrogen, the question is, does it stay a hydrogen with reduction, or does it become an oxygen with oxidation? Our ozone is this structure. So it's O3, so you have oxygen, single bond oxygen, double bond oxygen. The one with the single bond has a negative charge. The one in the middle has a positive charge. So what we're going to see, I guess, sorry, I'm trying to stay zoomed out in case you didn't write everything, but I guess, is everyone, did you get the oxidative part written? Okay, all right, so I'll zoom in. All right, so our nucleophilic side is the one that is negatively charged. Our electrophilic side is the one that is neutral. Because remember, when oxygen has a positive charge, you attack next door, right? We don't ever attack oxygen with the positive charge directly. We always attack next door. So we're going to see our alkene comes out and attacks the electrophilic side. We're going to then push the electrons onto the oxygen with a positive charge, right? Just like the normal, as if, you know, we're trying to, anytime we're attacking next door, you push the electrons onto oxygen. And then my nucleophilic side, that lone pair, is attacking the more substituted side of the alkene. That makes what is known as a malazonide, which is a primary ozonide. Basically, it's a 5-membered ring with 3 oxygens, is the idea. You get this wonky looking thing. This then breaks apart. So this is then going to decompose, where we're going to see that our electrons are going to push back down. We're going to actually cleave that carbon-carbon double bond, or sorry, cleave the carbon-carbon bond, forming a carbon-oxygen double bond. And then we're going to kick out this oxygen. So we are making 2 carbonyls and breaking one of the oxygen-oxygen bonds. That is this part. This is this part. If I just take this and flip it upside down, the idea is my electrophilic side of this aldehyde is the carbon. My nucleophilic side is the oxygen. The electrophilic side of this monstrosity on the left is the carbon attached to the double bond oxygen. My nucleophilic side is the O-. So by splitting it in half, I'm just flipping the aldehyde portion over, and then I click them back in together. So that the O- is what attacks out. So I start at the O-, I go to the carbon of the aldehyde, and instead of putting the electrons directly onto the oxygen, they're going to swing out and attack the electrophilic side of the thing on the left. And then that's where we push the electrons up onto that oxygen. That makes our secondary ozonide, which is just known as an ozonide. So a different 5-membered ring containing 3 oxygens. This is the product of step 1. So we get to this ozonide, and then we stop. Step 2 is what's actually going to break it apart and cleave it and like break it down into 2 carbonyls. So in step 2, and actually here, I'm going to keep the highlightings because I think that might help you to see where our elements are. So that's this. That's that. Right, so we just took it, and this is this part with that, and this is this part with this. Right, that's how we're just click it together, split it in half, click it together, and now we're going to split it in half again. So that sulfur, that is going to be nucleophilic, right? Sulfur was always nucleophilic, right? Anytime we had sulfur, we had said it was a strong nucleophile. Sulfur is also oxophilic. So sulfur and phosphorus are oxophilic, meaning that they are oxygen lovers. They love oxygen. They make really strong bonds to oxygen. So anytime you can make a sulfur oxygen bond, that's going to be beneficial. So, I mean, it was the same thing with like our thionyl chloride or that phosphorus trihalide. That was the same driving force, was that we were trying to get an oxygen sulfur or oxygen phosphorus bond. So that sulfur is going to attack this oxygen of my oxygen-oxygen bond. And technically, which one it attacks doesn't matter. You just got to make sure that you either push it like clockwise or counterclockwise. Because the key thing is that we're going to cleave this oxygen-oxygen bond. So we're going to break those electrons. We're going to give them from the oxygen-oxygen bond to make that double bond. That breaks the other carbon-oxygen bond and gives the electrons to the oxygen. So we're cleaving this thing and cleaving that thing. That freed our 1 carbonyl. There's my ketone product. Check. So then my aldehyde is going to form from having these electrons from that O- come down and push out that OSMe2. That makes my aldehyde. And then the DMSO is being formed because I drew it like this. That's the product of my arrows. That is just a resonance structure with that. So if I wanted to get to DMSO directly, then I would just need to have it actually going to the bond instead of to the oxygen. But it's just a resonance structure. And that's DMSO. That's our, the solvent DMSO, dimethyl sulfoxide. Are there any questions about that oxidation? Yes. I want the product of your arrows, so I want you to either draw the DMSO or the what's going to be known as an ylide, the charged intermediate, because I want to see that you know where the electrons are going. So yes, I want you to draw that product. Any other questions about the mechanism? All right, last one is our potassium permanganate. So this is our potassium permanganate. We're going to do the same sort of thing as that osmium tetroxide, where we're going to have alkene attacks the oxygen. We're going to push the electrons onto the metal. And then that O-, the nucleophilic side, is what's attacking the more substituted side of our alkene. The difference between the potassium permanganate and the osmium, with the ozonide, with the ozonolysis, is that, or actually even our osmium tetroxide, is that this is not stable. So that osmium intermediate is stable, right? We needed to add water in order to break it down. The manganate, that's a really reactive reagent. It doesn't stop. It keeps going. So it's going to actually immediately just fall apart as soon as it is formed, unless it's cold, unless there's something forcing it to stop here. So unless cold or dilute, it doesn't want to stop at the single bonds to the carbon and oxygen. So under normal conditions, this is what it wants to do. It actually wants to fall apart fully, where we're going to have the electrons from the oxygen-manganese bond push down. They're going to make the carbon-oxygen double bond. That carbon-carbon bond breaks, makes the other carbon-oxygen double bond, and then we're going to break the other oxygen-manganese bond, giving the electrons to the manganese. That makes our ketone and our aldehyde. But remember, from chapter 9, potassium permanganate is such a strong oxidant, it can oxidize these. So it will always oxidize all the way up to a carboxylic acid. So what it's doing is it is breaking that carbon-carbon double bond, and it's just everywhere where it can split it off, it will, to give you all potential carboxylic acids. So in summary, for these mechanisms, our cyclization is occurring with the oxidant. It is cleaving our alkenes, replacing them with oxygen. Ozone requires that reductant or oxidant in the second step. And potassium permanganate will always go the whole way to carboxylic acids. Any questions? All right, have a wonderful weekend. Oh, and I have, if you were a Tuesday recitation, I have your regraded exams. Hey, what's up?